A spacecraft launched nearly 50 years ago, running on less power than a refrigerator light bulb, just sent back a transmission from 13 billion miles away. And buried inside that data is a warning that took scientists years to fully understand. Voyager 2 has been traveling since August 20th, 1977. It outlasted the slide rules its engineers used to design it. It outlasted the careers of most people who built it. It flew past Jupiter, past Saturn, past Uranus, past Neptune, becoming the only human-made object to study all 4 of the solar system's giant planets at close range. It discovered 14 new moons, 10 new moons at Uranus alone, and 2 new rings around that same distant planet. Then it kept going, deeper and farther, until on November 5th, 2018, it crossed the heliopause, the outer edge of the Sun's influence, and became only the second spacecraft in history to enter true interstellar space. At that moment, Voyager 2 stopped being a spacecraft exploring our solar system. It became humanity's first outpost, in the space between the stars. And what it has been transmitting back ever since is a warning up. The world is only now beginning to take seriously. To understand the warning, you need to understand what Voyager 2 is actually sitting inside right now. Our sun does not simply shine, it breathes. Every second, it exhales a continuous stream of charged particles called the solar wind, blasting outward in all directions, at speeds between 1 and 3 million miles per hour. That solar wind does not stop until it runs head first into the material, filling the space between stars, a region called the interstellar medium. The collision creates a vast bubble around our solar system. Scientists call it the Heliosphere. Inside that bubble sit all 8 planets, all the moons, all the asteroids, all the comets, and every human being who has ever lived. The Heliosphere is not just a feature of our solar system. It is a shield. It deflects and absorbs the majority of the galactic cosmic rays, which are high-energy particles produced by supernovae and other violent events scattered across the Milky Way. Without it, the radiation environment inside our solar system would be dramatically more hostile to life. Voyager 2 crossed the outer wall of that shield in 2018. What it found on the other side is the source of the warning. Before the crossing, as Voyager 2 approached the heliopause in the autumn of 2018, its cosmic ray subsystem instrument began detecting something significant. The rate of cosmic rays striking the spacecraft increased by around 5%, compared to readings from just weeks earlier. Then it climbed further. The energetic particles streaming in from the galaxy were intensifying as the spacecraft approached the boundary, piling up at the outer edge of the heliosphere like waves building against a seawall. On one side of that wall, the sun's influence thinned to almost nothing. On the other side, the full force of the galaxy waited. The moment Voyager 2 crossed the heliopause, the reading changed dramatically and almost instantly. Cosmic ray levels surged. Solar wind particle counts dropped sharply. The plasma surrounding the spacecraft shifted. From the hot, thin, fast-moving material of the solar wind to the cold, dense, slower-moving material of the interstellar medium. The boundary was not a gradual fade. It was a sharp line, thinner and more precisely defined than scientists had predicted, and crossing it meant entering a completely different physical environment in the span of days. The data that came back from those crossing measurements, published by 5 separate scientific teams, simultaneously in the journal Nature Astronomy in November 2019, laid out the picture with brutal clarity. The heliosphere's outer wall is razor thin. The interstellar magnetic field pressing against it is 2 to 3 times stronger than models had assumed. The pressure from interstellar plasma and cosmic rays on the outside of the heliosphere is up to 10 times greater than calculations had predicted before any spacecraft had actually been there to measure it. These are not minor adjustments to existing theories. They are discoveries that required scientists to fundamentally revise how they think about the structure and stability of our cosmic shield. And that is the first part of the warning. The shield works. It has protected life on Earth for billions of years, but it is being squeezed by forces an order of magnitude more powerful than we calculated when we had no instruments outside the heliosphere to check our math. The heliosphere breathes with the sun's 11-year activity cycle, expanding slightly during solar maximum when the sun's output peaks and contracting during solar minimum when it dips. Scientists now know that those fluctuations, combined with the stronger than expected external pressure, mean the boundary of our cosmic shield shifts in ways that affect how much galactic radiation leaks through into the inner solar system. Over short timescales, this is not a crisis, but over geological timescales, over millions of years, changes in the sun's long-term output or in the properties of the interstellar medium our solar system is currently passing through could shift the heliosphere's boundaries significantly. Research published in recent years has explored the possibility that past periods of elevated cosmic ray exposure on Earth, caused by a weakened or compressed heliosphere, may have left detectable traces in the geological record. The warning is not that the heliosphere is about to collapse. It is that it is less stable and less impervious than we assumed. And we only know that because Voyager 2 told us. The second part of the warning came in March 2025, when NASA confirmed it had been forced to shut down 2 more science instruments across the Voyager spacecraft, one on each probe, to conserve their dwindling power budgets. Voyager project manager Suzanne Dodd stated plainly that without those shutdowns, the probes would probably have had only a few more months of power before NASA would have needed to declare end of mission entirely. The 2 instruments shut down were Voyager 1's cosmic ray subsystem, a suite of 3 telescopes that had helped confirm when and where the spacecraft exited the Heliosphere, and Voyager 2's low-energy charged particle instrument, which measured ions, electrons, and cosmic rays originating from both the solar system and the galaxy beyond. These were not redundant systems. Each instrument provided a unique category of measurement that no other instrument on board could replicate. Their loss narrows the scientific picture Voyager 2 can send home, and it narrows it permanently. Those instruments are not coming back online. The data they would have collected as the spacecraft moves deeper into the interstellar medium is simply gone. As of 2026, Voyager 2's cosmic ray subsystem is also scheduled for shutdown this year. When it goes dark, Voyager 2 will be left operating only its magnetic field and plasma wave instruments, just 2 scientific eyes looking out from 13 billion miles away into a universe our other instruments cannot directly touch. Engineers at NASA's Jet Propulsion Laboratory believe the remaining instruments can continue operating into the 2030s if no unexpected technical failures occur. But they acknowledge the same thing in every public statement about the mission. The Voyagers have been weathering deep space for nearly 50 years, and unforeseen challenges could shorten that timeline at any moment. Every transmission is potentially the last one. And every transmission is irreplaceable, because no other spacecraft is heading toward the heliopause on a trajectory that would reach it within any meaningful time frame. This is the third and perhaps most profound part of the warning. When Voyager 2 goes silent, humanity will have no instrument in interstellar space. None. The region outside our solar system, the environment that presses against our cosmic shield from every direction, will go dark to our measurements. Scientists will be left studying the heliosphere entirely from the inside, like doctors trying to diagnose the condition of a patient's immune system without being able to examine anything outside the body. The Interstellar Mapping and Acceleration Probe, known as IMAP, launched in 2025 and is studying the heliosphere from a stable orbit near Earth. It contributes valuable data, but it is not in interstellar space. It cannot measure the direct properties of the interstellar medium the way the Voyager instruments can. An actual interstellar probe mission, one designed from the start to travel to and beyond the heliopause with modern instruments built for that environment, has existed in NASA planning documents for years. The science case is unambiguous, but designing, funding, building, launching, and flying such a mission to the outer boundary of the solar system would take decades, even if approved and funded today. Anyone who voted to start it now would not live to see its primary results. In the meantime, Voyager 2 keeps transmitting. Its signal arrives at the giant dishes of the Deep Space Network, the Australian station in Canberra primary among them, with a power level unimaginably faint. The entire received signal is billions of times weaker than a single pixel of light from a distant star. Engineers filter it, amplify it, decode it, and extract from it numbers that describe conditions in a place no human instrument has ever reached before, and may not reach again for generations. Each number is a data point in a scientific picture of the interstellar environment that will shape research into planetary protection, long-term climate on Earth, and the fundamental physics of how stars and their planetary systems interact with the galaxy around them for decades after the last transmission fades. Voyager 2 sent this transmission and warned the world not with dramatic language, not with coded signals, not with anything resembling what viral headlines promise. It warned the world with data, cold, precise, peer-reviewed data that showed the cosmic shield. We live inside is under greater pressure than we knew, that the interstellar environment surrounding us is more turbulent than our models assumed, and that the one machine capable of measuring it from the outside is running out of time. That is the transmission. That is the warning. And the most unsettling part is not what it said. It is that once Voyager 2 goes quiet, we will have no way of knowing what comes next. There is something about this spacecraft that does not fit comfortably inside the usual categories of space exploration. It was built in the mid-1970s by engineers who had never done anything like it before, using technology that would embarrass a modern pocket calculator, powered by a radioactive core slowly burning itself out one atom at a time. It was designed to last 5 years and complete a flyby of Jupiter and Saturn. Instead, it has lasted nearly 50 stars, traveled to all 4 of the solar system's giant planets, discovered 24 new moons, confirmed the existence of a geologically active moon of Jupiter called Io, with active volcanoes erupting as Voyager flew past, surveyed the twisted magnetic field. Of Uranus, discovered 6 new moons and 4 complete rings at Neptune, and then sailed on past everything it was built to study into territory no instrument had ever entered. The fact that it is still transmitting at all is a form of engineering miracle that scientists at JPL describe with barely concealed emotion. But the data it is sending back is not miraculous in the comfortable sense. It is miraculous in the sense that it forces us to see something true that we would rather not have known. The interstellar medium outside our solar system is not the quiet, empty void that older science imagined. It is active, turbulent, dense with plasma, threaded with magnetic fields stronger than our models predicted, and pressing against the outer walls of our heliosphere with a force that caught the scientific community genuinely off guard when Voyager's measurements confirmed it. Every kilometer, Voyager 2 travels deeper into that environment, roughly 15 kilometers every second, adds to the map of a region that will determine our scientific understanding of how the heliosphere truly works for the next generation of researchers. The warning is real. The data is confirmed. The instrument sending it home is almost out of power. Listen while it still transmits. Consider what it means that scientists discovered the heliosphere's outer wall is thinner and the external pressure against it is far stronger than expected, and that they only discovered this because a spacecraft launched before most people alive, today we're born, happened to still be functioning when it reached the boundary. We had models, we had theories, we had sophisticated computer simulations based on the best physics available, and they were wrong by an order of magnitude about the forces pressing against our shield from outside. That is not a failure of science. That is exactly how science is supposed to work. You build the best model you can with available data. You test it against reality, and when reality contradicts the model, you revise the model. But the lesson embedded in this particular correction is uncomfortable. We had no data from outside the heliosphere for the entire history of human civilization until 12 years ago. Everything we thought we knew about the interstellar environment pressing against our solar system was theoretical. Voyager 1 gave us the first real measurement in 2012. Voyager 2 gave us the second in 2018 from a different direction, confirming and extending what the first had found. 2 data points from 2 aging spacecraft are the entire foundation of our observational understanding of the very local interstellar medium. 2 data points are not enough, but they are all we have, and they have already changed the picture dramatically. Voyager 2 warned the world not by discovering something alien or catastrophic, but by revealing that the universe surrounding our small, protected corner of the galaxy is stranger, more powerful, and more relevant to life on Earth than we ever had the instruments to know before.